for this third chapter, until 10, computing the different Galois. So we have seen that given a difference equation, we can associate a Picard extension that measures that contains the solution of this equation, and we can also associate a group, the Galois group, that measures the algebraic relation theoretically. So in practice, how do you compute the Galois group? So let's remark that in general, compute the Galois group is difficult. There is an algorithm made by Feng, which is an adaptation of the Dreyfus algorithm in the different case, that computes it in general, theoretically. I say theoretically because the complexity of the algorithm is so big that in practice you cannot apply. So we'll give you some concrete algorithm in a very particular case. I will only sketch things here. I will not give a complete proof. So the first case is a case of sequences, and we will recover the algebraic relation satisfied by the Fibonacci sequences. Remember that it was the motivation of this course. So we are in framework of sequences, and let y. So it's a vector of sequences, which is solution of a difference equation, a shift difference equation, with a matrix A having coefficient in C. Okay. We can embed y into a Picard extension. So it will permit to understand the algebraic relation. But we will not consider the Picard extension corresponding to y. We'll consider an abstract Picard extension. So which will be isomorphic to the one with y inside. So I remind that two Picard extensions are isomorphic. So I consider this sequence of matrix, and it's obviously a fundamental solution. And moreover, we can prove that it generates Picard extension. So in other words, we don't need to question by maximal sigma either. So remark that sigma acts on the Galois group. So sigma is obviously commutes with sigma. It's a ring automorphism of R, and it is the field of constants invariant. And since the field of coefficient is the field of constants, so it belongs to the Galois group. And I told you that sigma of u equals u times I, so it means that the matrix associated to it is the matrix I. So let me call A with brackets the group generated by A. And remind that the Galois group is an algebraic group, so this group may not be an algebraic group. So it's a Zariski closure. Which is the smallest group, algebraic group, containing A. So since the Galois group is an algebraic group, which contain A, we have the Zariski closure is contained in the Galois group. But we want to prove the converse now. So so remind that K is the direct sum of integral domain. And the total PV ring is the direct sum of the field of traction. So it's the direct sum of field. And so since sigma corresponds to A, it means that if you consider the subfield of K invariant under A, it's a field of constant, so it means that it's just C. And in fact, we can prove, but it's not a trivial fact, that the same hold for the Zariski closure. So Galois correspondence implies that A is the Galois. So to compute the Galois group, so we need to compute A, and algorithm exists for such a task. It highly depends on the Jordan decomposition of A. So I will sketch the algorithm in a particular case. When A is diagonalizable. So let us write A equals P d P minus 1 and with the diagonal matrix. So we have that the Zariski closure of A equals P times the Zariski closure of D times P minus 1. So it's a group, and you just multiply the element of the group by P to the left and P minus 1 to the right. And so we can compute D in general if we know the multiplicative relation among the eigenvalues. So the complicated task is not to compute the group generated by D, but the Zariski closure of it, because you have to understand what is a small group. But you will see that in some cases it can be done. So, for instance, take the Fibonacci sequences. So let me give you the eigenvector and the eigenspace and the eigenvalue, sorry. And you can check. So the group generated by D is a group of diagonal matrices. So its Zariski closure is the same. So the off-diagonal coefficient has to be 0. And the diagonal coefficient just satisfies the following equation. And so you can very concretely find the relation satisfied by the entry of the matrix. And it can be done by hand. You need a computer. But for instance, so you can also consider the following fact. With a computer, compute the algebraic relation between the Fibonacci sequences and -1 to the n. And then you find the relation that I've given to you at the very beginning of the talk, so the course, sorry. So you can treat any example. So I've given to you how to do it when the matrix is diagonalizable, but it can be done in full generality. And you may also consider several sequences, solution of several equations, and try to understand what are the relations between them. And everything is totally algorithmic. Let me continue this algorithmic consideration with the case of Hendrik's algorithm. So let me express this in the case S with n equals 2. So n equals 2 is the main framework of Hendrik's algorithm. So remember that there was a theorem that says that you may transform a system with a Gauge transformation with a system inside the Galois group. So the goal is to use this theorem. So the goal is to find a Gauge transformation to reduce the system. So let's consider another two equations. And you know that right? You know that it's equivalent to the system so, and consider the Galois group. So A and B are in C of Z, and of course B is not zero. And then this matrix is in that sphere. So it's a subgroup of GL2 of C. And how to compute J? So J is an algebraic group of GL2. And remember that J over J0 is cyclic. So it's two information. And with the classification of the algebraic subgroup of GL2 of C, we find that three situations occur. The first one is the following. So remind that J is conjugate is defined up to conjugation. So J is conjugated to a subgroup of triangular matrices. The second case, J is conjugated to a subgroup of the infinite J-dual group. And the case 3, J contains SL2. So I leave you a little exercise. So that J is an algebraic subgroup of C star and is the difference Galois group of sigma of y that the A times y and it's B. So remark that algorithm for computing Galois group of order 1 equation exists. So you have concrete criterion on B in order to ensure that this is C star or proper subgroup of C star. So let's treat the case 1. So case 1, if and only if there exists u, a rational function, such that u sigma of u plus a u plus b equals 0. And work on, so it's called a Riccati equation. And it's equivalent to the fact that there exists y solution of the first equation and the second one. So it's a situation where your equation is factorizing. So sigma y plus ay, a sigma y is of the form sigma of b over u times sigma minus u. So you have a factorization of your operator. And we mark that Petkov-Shek gave an algorithm to solve the Riccati equation. So you have very concrete criterion on the coefficient of your equation to ensure that you are in case 1 or not. And Hendrix give a similar criterion. So to the case 2 is equivalent on the fact that there exists u solution of a Riccati equation for sigma square and with other coefficient. And so Hendrik push forward this kind of argument. Hendrik use this kind of argument to compute J. So not one thing that solving a Riccati equation is not so easy. So it can be made algorithmically, but the complexity is exponential in the order of the equation, so and the degree. So it's not easy. It can be done, but it's not easy.